All right. So, people are coming. I'll share my screen. Ouch. Know what? I might need to reconnect. I updated my Zoom. No, it's fine. Updated my Zoom and it required a new plugin to share the iPad screen, but apparently, yes, everything works. Awesome. So, so here we are. And I want to start with this theorem that's highlighted. And by the way, just a second, I'll open chat just in case. And I went a little bit too fast about this non-obvious part about measure of psi of O. So I'm going to prove it again from the very beginning. So I'm going to remind that we have our counter set C. We have O equal to 0, 1 minus C. And we have psi of X equal to X plus phi of X, where phi is the counter function. So we want, this is actually the goal, we want to prove that the measure of the image of psi of O is equal to 1. Okay, so let's recall what is O. So O is the union of OKs, and OK itself is the union of IK1 with IK2 with blah 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 with IK2 to the K minus 1. Oops. Okay, not sure what happened. Froze for you, yes. Luckily, I didn't tell anything new. Wait just a second. All right. Let's try with an open door. Resume share. Okay. So one thing that could have went wrong is that when I close the door, maybe the signal is not so good because I'm on the second floor and the main router is on the first floor. So do you hear me now? Okay, yes. Hopefully you do, yep. Okay, so I opened the door, which means that my daughter will think that she's welcome to come in, but other than that, we should be fine, hopefully. Okay, so here's the goal. I just, the only thing I did is that I wrote what do you want to prove, and then I reminded the notation. So OK is this union. This was the last thing I wrote, and then phi was defined like this. So if we restrict phi to I m k, then it will just be a constant, m divided by 2 to the k. So on each I k m, phi is a constant. So let's see how psi acts on these i's. So if x is an I k m, then psi of x is just x plus m over to the k.
You aren't currently sharing your screen.
I'm not.
You're stuck on frozen right now. All we see is.
Okay, that's interesting. because it shows that I do. Okay, so let's stop. Let's do a new share. What about now?
Still
No, last thing I see is OK equals I.
same.
Ah. Okay, that's unexpected. So let's try to stop share here and then share again. What about now?
That's good.
Okay,
Yes, updated.
so yeah, the problem is that I'm keeping chat in the corner. They don't always see it. Okay, so it's better now, right?
Yeah.
Yes.
Okay. Let's see. Yeah, so I'm running literally nothing on my computer, so there's nothing that should slow down. I can close Firefox, but not sure it will really help. Okay, well, let's try. Let's see how it goes. Okay, so yeah, so the last thing I wrote were these two lines. That if we restrict phi to one of the i's, then we have this formula. This was just the definition. And so if x is in one of these intervals, if x is an ikm, then psi of x, because psi of x is x plus phi of x, and phi of x is this, so we get that psi of x is x plus m over 2 to the k. So my point is, I'll just write it in formally. My point is that the image of IKM is IKM shifted by m divided by 2 to the k. Right? Because psi on IKM acts almost like a linear function. So if you cross out what's circled here, then psi will be just equal to x. So if the thing in the circle didn't exist, then psi of IKM would just be the same as IKM. But because we have this circle term, which doesn't depend on x though, when x is an IKM, then we should shift IKM. So see who was right. Вика, я открыл дверь, потому что иначе интернет ломается. Но ты сейчас должна уйти немедленно. Что? Prodigy? Надо в гугле набрать Prodigy. Okay, sorry about that. We're figuring out homeschooling with a 7-month-old and almost 6 years old. So, yeah. Okay, yeah. So I kind of explained why this sentence, my point is, works. And this implies, so because the Lebesgue measure doesn't care about shifts, so Lebesgue measure of a shifted set is the same as the Lebesgue measure of the original set. This implies that measure of psi of IKM is equal to the measure of IKM. Oops, sorry. So measure of image of psi is equal to the measure of the interval. And this implies, because IKMs are disjoint, IKMs are disjoint, and psi is 1-to-1, because it's strictly increasing, we get that psi of IKM, these sets are also disjoint. when we change m and not k. So when k is fixed. And so this really helps us to measure psi of OK. So now I will measure psi of OK. So OK is psi of ik1 union blah 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 union ik to the k minus 1. Now these fellows, so that's a disjoint union, and psi is 1 to 1. So this is a rare case when psi of the union is equal to union of psi's. Typically that's not true. Typically this is true for the pre-image, but not for the image. But because psi is 1 to 1, it's fine. So that's sum of the measures. Yeah, so I need to write it a little bit more carefully. So it's M1 of the union, like this. And now these fellows are disjoint, so measure of the union is sum of the measures. So we get sum of the measures. Sorry, psi of ikm m from 1 to 2 to the k minus 1. And we know from here that measure of psi is the same as if we drop the psi. So we just get the sum without psi. And this is the measure of OK. So this is what I rushed through last time, that measure of psi of OK is the same as measure of OK. And now, because we have this relation, this implies that measure of O is equal to the limit of measures of OK, and this is equal to the limit of measures of psi of OK. And again, because psi is increasing and 1 to 1 and everything like that, these sets are also increasing, and they increase to O, to psi of O. So the limit here is in K. There is no M anymore, except for the Lebesgue measure. And so what we got is that measure of psi of O is equal to the measure of O. Okay, but measure of O is equal to 1 minus measure of C, and we know that measure of C is 0, so measure of O is 1. So measure of psi of O is also 1. And now recall that psi maps 0, 1 to 0, 2, and psi of C, because C and O are disjoint, is the same as 0, 2 minus psi of O. And so this implies that the measure of psi of C is also 1. So I already don't remember, but someone asked if I am going to prove this. Well, yes, but this kind of follows more or less easily from all this previous work. Okay, so any questions about this proof? So the proof is done. There were some more results about psi, but they were all obvious, like it was strictly increasing.
Is I don't know. It's probably just because this is an example of a really bad, ugly function. You put in measure 0, you get a measure of 1. Like, the fact that the function's 1-to-1 and onto on the Cantor set, do we need to worry about that?
No. So you don't need to worry about anything. So yes, it's 1-to-1, but it fattens the set still. So Cantor set is, so I kind of see what you're asking. You're asking how can a really decent continuous 1-to-1 function map something of measure 0 to something of measure 1. Probably that's what
Yeah.
you're asking. So the reason is that Cantor set, even though it's of measure 0, but it's almost of a positive measure. So if you have, say, a countable set, it's very, very small. So it's of measure 0. Well, like even countable set, if you fatten it just a tiny bit, you get something of positive measure, but countable set is too small. Cantor set has lots and lots of points, so it's uncountable. And so it from the very beginning had a decent chance to have positive measure. The way we chose these intervals or their lengths forced it to have measure 0. But if you just stretch these intervals a little bit, or yeah, so like if you stretch the intervals that form the Cantor set a little bit, you start getting a non-zero measure. So this is probably what Psi does. So it's increasing in 1-to-1, but it's still allowed to stretch, right? It's not an isometry. It doesn't preserve distances, and so this is why it does that. But it's very anti-intuitive. So I cannot really draw a decent picture and explain why it does so. You can try to Google, maybe there are some animated videos about this Psi, but I'm not aware of one. So I really cannot explain how Psi actually works, except that I know that Cantor set like had a better chance to have positive measure than a countable set, for example. So, but here's another thing about Psi. So I'll state the corollary, and you'll be even more surprised. It won't explain anything, but it will show you what else can happen. So corollary is that there exists a measurable set whose image is not measurable. Which also should be surprising because Psi, after all, is a nice continuous function. So it's first of all continuous everywhere. Second of all, it's increasing, strictly increasing. So we know that it's almost differentiable. We already learned that an increasing function is almost everywhere differentiable. And yet it can map a measurable set to a non-measurable set. Which to me is a little bit surprising. Okay, so how do we prove it? Well, to prove it, we need a fact that I said that I'll skip. So remember when we did non-measurable sets, I proved that there is a non-measurable set in 0, 1. So now I need another fact, which is proved in Royden and whose proof is absolutely the same. So the fact is that any set of positive measure, Lebesgue measure, I mean, of course, contains a non-measurable set. Okay, so I won't prove it. The proof is absolutely the same. You can run the same proof. I never actually used that. We're working on the interval 0, 1. I only used it in the proof because I needed it to be bounded. But if you have a set of positive measure, you can always take a really huge interval such that the intersection of this set of positive measure with a huge interval will also have positive measure. And then your set is bounded. Okay, so now take psi of C. So this is a set of measure 1. So this is a set of measure 1, which means that there exists a non-measurable set. In psi of C. And finally, we'll take A, which is equal to the pre-image of B. Well, B is in psi of C, so pre-image of B is in C. And by completeness, so what do we know about C? We know that C has measure 0. Oops. So measure of C is 0, therefore, that's a 0, that's not an O. Therefore, by completeness, A is measurable. So we know that our Lebesgue measure is complete. So if we have a subset of C, then A is measurable. Okay, but just by our notation, psi of A is equal to B, which is not measurable. And that's it. So psi, like the reason for this corollary is again the same one we discussed. So it was actually a good question that psi really fattens sets of measure 0. So psi can take a set of measure 0, like C or A in this case, and perturb it a lot. Even though it's increasing, it's still like it still adds a lot of chaos to the set, and so it can make a positive measure from a 0 measure. Sorry, not enough sleep. And or it can make a non-measurable from 0 measure. So this psi is really weird. And the reason we're doing all this is the following very important result. So we discussed it a little bit. So we will now denote by B, and this is a fractured B, the minimal sigma algebra that contains all open sets. And by minimal, I mean with respect to inclusion. So B, so anything, so if we have another sigma algebra that contains all open sets, then B should be a subset of this second sigma algebra. And so what I want to prove, and I kind of advertise this, is that B is not equal to M1. So M1 is bigger. We know that M1 contains all open sets. Okay, we know that any open set is Lebesgue measurable. We know that any open set is Lebesgue measurable, and because B is minimal, this implies that B is contained in M1. So the question is it true that B is equal to M1? Well, the answer is no. So here's the proof. And the proof, I'll use the following fact that I'll leave as an exercise. And the fact is that if we have a set in the sigma algebra, then psi of A is also in this sigma algebra, which is called Borel sigma algebra, by the way. Borel sigma algebra. So M1 is called Lebesgue sigma algebra, and B is called Borel sigma algebra. Okay, so this arrow is true because psi is continuous and increasing. And like, you need to think about what does it mean for an A to belong to B. It basically means that A is, let's see, it's either intersection of unions of open sets or union of intersections of open sets. But A is something like this, and psi preserves both unions and intersections, and psi preserves the openness condition, which is important. So psi of A also must belong to B. Okay, so I'll leave it as an exercise. Encourage you all to do this. That's almost a qualifying level exercise. Okay. And now, so after we believe in this fact, we're almost done. So now take A in C such that psi of A is not in M1. So if A was Borel measurable, just a second. Я прислал message. Sorry. If A was Borel measurable, then it would imply by the exercise that psi of A is Borel measurable, and Borel sets are all Lebesgue measurable sets, and that's a contradiction. I should be a good boy and write this without the arrow. If A was Borel, then psi of A would also be Borel, but then psi of A would also be Lebesgue measurable, but it's not. So
can we
yep.
have an open set in C?
Can we have no? Good question, no. So C is so C has many properties that give a negative answer. In particular, C is what's called nowhere dense, and you'll see it in the second homework I've sent. But also C cannot contain any interval, because imagine what we're doing to obtain C. We take whatever interval we see, like in the steps, and there is the middle third. So eventually C becomes free of any like solid intervals, because if there is an interval in C, then eventually we will erase part of it.
So how do we know that we can have an A contained in C that's in our Borel sigma algebra?
We don't. But if okay, that's the point. We definitely know that A is an Lebesgue sigma algebra. Okay, because Lebesgue measure is complete, and so if A is a subset of measure 0, then A is in Lebesgue sigma algebra.
Okay.
And what we achieved in these two lines is that A cannot be in B. So A is Lebesgue measurable, but it cannot be Borel measurable. You're absolutely right. That's the point. that A cannot be in B. At least sometimes. So this was exactly the point of the theorem, that B is not equal to M1. If B was equal to M1, then this would imply that A belongs to B, but it doesn't. Okay, I'm frozen, right?
The last thing I see is contradiction.
Yep,
Yeah.
the same. Curiously, it's also the last thing I see, but I hear you and you apparently hear me. Okay, this update to Zoom maybe wasn't the best. Okay, now you should see everything, right?
Okay.
Yeah,
Yes.
so my point, so the whole point was that A is in M1 because the measure is complete, but A is not in B because otherwise psi of A would be in M1. And so we found an A which is in M1 but not in B. And this proves that B is not equal to M1. If B was equal to M1, then M1 and B would share all the sets. Okay, so the good news is that we're practically done with the qualifying material. So we'll continue doing measure and integration, and in fact what we will be doing now should be in this first part of the course, but this Cantor set was more or less the last topic, the last qualifying topic, the last qualifier topic. So what we'll do next, I believe, is not in the qualifier curriculum. Let me actually try to find it. Yeah, my internet not the fast today. Yeah, so for real analysis, yes, yeah, so I'm right, which makes sense because I wrote this list, but what we're going to do next is not one of the qualifier topics. So for those of you who are only interested in the qualifier, you can relax a little bit. But on the other hand, those of you who will take measure and integration 2 in the fall, again with me by the way, you shouldn't relax. But another important thing, that everything that we've done before this point can be on the qual, including Cantor set. So Cantor set is actually a very famous qualifier topic, because as you've already seen, it produces lots and lots of very weird examples. And weird examples is what you very often see in the qual. Okay, so now we move on to another very important result, which is called Redon-Nikodym theorem. And this Nikodym is very hard to spell. So it has an I and a Y, and it's hard to remember where is I, where is Y. So if I make a mistake, sorry, but this time it's correct. So that's the correct spelling. If I ever spell it differently, you can tell me. And this Redon-Nikodym theorem builds up on this fact that we've learned, that if a measure of A, or whatever, actually any measure of A0 implies that the integral of a decent function over A is also 0. So the point of Redon-Nikodym theorem is to kind of prove the converse. So the main goal, which by the way will be pretty hard to achieve, so we won't do it today, but just so that you know what are we trying to do. So the main goal is to prove the following: that if we have another measure that satisfies this arrow, so if mu and nu are two measures such that measure of A equal 0 implies another measure of A is equal to 0, then nu of A is an integral for sorry, for some f. So not only this arrow holds, but basically it's the only case when it holds. So if we know that mu of A implies that if we know that mu of A equals 0 implies that nu of A equals 0, then we know that nu of A can be computed as an integral of some function. So for some f, that does depend on A, of course. That does not depend on A. So this, what was called absolute continuity, I think. Well, absolute continuity was a little bit different, but along the way, we'll prove that this relation is kind of enough for absolute continuity. So this absolute continuity is satisfied only for integrals. There are no other pairs of measures. Okay, so this is the goal. It's actually pretty important for some applications, and we'll also do it in a more general case. We'll do it in the case when nu is allowed to be what's called a signed measure. So nu will actually be allowed to take negative values, and so therefore f will be allowed to take negative values. However, as soon as we allow our measure to take negative values, we should be very, very careful about the countable, what was it called? Well, countable monotonicity, for example, or countable additivity. Yeah, so because in countable additivity we had a series, and for a regular measure, for a nice measure, this series at least had positive terms. I didn't open the chat, by the way, so hopefully I didn't disappear. Yep. So this series had positive terms. Now we will allow our measure to take negative values. So now this series will be allowed to have negative terms. And so the convergence will be a little bit harder. So here's the definition. Well, here's the setting. So let x and A, so we're back to our general setting, be a space with a sigma
I'm not seeing
algebra.
anything on the screen.
Again, yeah, that's true. Well, the good thing is that I didn't write. I wrote almost nothing. Okay, but now I know how to heal it. Just start sharing. Okay, yeah, thank you.
And, I got confused when we were talking about, so we're now trying to prove that mu of A equals 0 implies nu of A equals 0?
No, so I'm proving that this arrow implies that nu is an integral. So first of all, we'll start proving it, definitely not today and maybe even not on Monday, and when we do, I'll state it formally. So let me try to state it more formal. So I'm assuming that I have two measures. Let's for a while assume that they're both like regular, nice, positive measures. And we know, assume that if mu of A is 0, then nu of A is 0. Then the conclusion is that then there exists a function f, a non-negative, measurable, blah, 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 such that nu of A is equal to the integral of f over A d mu for every measurable A. So this is what's our ultimate goal. So if we have this information for any A, then we know this. So here's a very simple example. Let's say that mu of A is, let's say, 1/2 times mu of A. Then we know this. I'm going to highlight it. Then we know this, right? Because if mu of A is 0, then mu of A is 0 divided by 2, which is 0. And then how do we cook this function? Well, then this function is just a constant. And so if we integrate 1/2 over A, we get 1/2 times mu of A. So the goal is to prove it for a bigger class of measures.
Okay, that's what we're gonna try to do now, or that's what we're gonna try to
No.
do some week.
No, if we do it by Friday, we'll be lucky.
Okay.
So now we will. So now the first goal is to state something like this, or at least learn how to state something like this when nu is allowed to be negative. So when this is not an honest measure, when this is actually allowed to be negative, but still has this additivity property. So first thing I need to do is to define what do I mean by additivity now. Okay, I actually can probably do it. Okay, I always struggle to do this. Whatever. There is some way. I tap, yes, I tap. Okay, delete. Cool. Okay, so here's the formal talk. Now everything is going to be clear. So let's say we have a space with a sigma algebra. Okay, not freezing. With a sigma algebra. So we call. So I'll also let nu be a map from A to the fully extended real line. So both minus infinity and infinity are allowed. But actually not really. So now I'll start adding restrictions. So we call nu a signed measure or sometimes it's called the charge. So charge comes from physics, obviously. If three things. So first of all, nu of an empty set is 0. Second, nu can't be both plus and minus infinity. By which I mean that if, for example, there is a set A such that nu of A is plus infinity, then nu is never equal to minus infinity. So nu has to decide from the very beginning what does it want to do. Does it want to be equal to plus infinity, or does it want to be equal to minus infinity? Yeah, and finally, 3, it will be the countable additivity. So if we have a disjoint collection of sets, well, kind of measurable, disjoint in A, then we still have the additivity property with a very important extra assumption. And moreover, if nu of the union is finite, then the series converges absolutely. EK, sorry. EK. EK. So before, I just want you all to compare this to the actual measure. So, well, property 1 is satisfied for a regular measure. Property 2 is also satisfied for regular measure because a regular measure cannot be minus infinity. So 2 is fine. Property 3 didn't need this moreover because property 3 for a regular measure means that this sum of nu of EKs is finite if nu of the union is finite. And if sum of positive terms is finite, then it converges absolutely, just because with absolute value or without absolute value doesn't matter. By the way, less than infinity and bigger than minus infinity. But now we add this really important property that if this is true and if everything is finite here, then the series on the right hand side actually converges absolutely, because theoretically it could just converge. It could converge conditionally. And we kind of allow conditional divergence. Okay, so if this is infinity, then we don't care. But if this is finite, then we won't allow conditional convergence. Okay, and one more definition. So we call a set A in the sigma algebra positive with respect to nu, which will probably drop because it will be obvious with respect to nu. If not only nu of A is positive, but if any subset of A has positive measure. If for every E in A, if for every E in A, I'll state like this, we have E is measurable, implies nu of E is non-negative. And we call a null set if for every E we have nu of E is equal to 0. Okay, and I need to finish, but why do we need this? Because we're going to prove, so our first goal is to prove the following, that if we have a signed measure, if we have such a nu, then we can split X into two parts, and one part will be a positive set and another part will be a negative set. So in fact, any signed measure nu is just basically a difference of two honest measures. And so this will be our first big goal. It will take a while to prove. It's actually not so easy to cook this positive set. But this is what we'll do. It's not even clear, and this is what I encourage you to think about over the weekend. It's not even clear that a positive set exists, because we have this pretty strong condition that for every E, this should be satisfied. So it's absolutely not clear that a positive set exists, but it does, and there exists kind of a master positive set, and this is what we're going to do. So I will create another meeting, which will be office hours at about 11:02. So I'll have office hours today. If you want to come, you're welcome to join right now. Unfortunately, I'll probably have to run away because there's some action going on downstairs. So I'll run away now, but I'm creating another Zoom meeting on Canvas for the office hours. And I'll see you either then or on Monday.
Okay, sounds good. Thank you.
Yep, thank you. Bye.
Bye.